All right, so just kind of reviewing some of our notes from yesterday. We're going to find the area under the function f of x on the interval from a to b. So we're going to break up that interval from a to b into n total partitions. We're going to break it up into n different portions. The width of each of these portions, the change in x, I have to add on to go from one partition to the next is given by delta x, or change in x. If I break up the total interval from a to b, the difference in b and a should tell me how far it is from a to b. I'm going to divide that difference into n total pieces, n total partitions. So the delta x, the change in x, the length of each base, all of these rectangles given by delta x, is the difference in our two endpoints, b minus a. How far is the total interval divided by n total partitions? That tells me the base length. Now, if we're using rectangles, I need to find the height of each of these rectangles. To find the height, we're going to use right endpoints, so that my first partition starts with a value of 1. So I start from A, I add on delta x one time, whatever x value that is, into the function. There's the height of your first rectangle, right? Now keep doing that. For the next partition, for the next rectangle, we're going to start from our left endpoint. How many delta x's do I have to add on to get to here? 2. I add on delta x to go from the first partition, then another delta x to get to the next partition. I add on delta x a second time. Whatever that x coordinate is, plug it into the function, its height on the curve is given by that, and I have the height. We're going to do that n total times until I get to the very right end. This coordinate, plug it up into the function. There's the last rectangle. So a way to figure out what x coordinate I have to plug into my function is given by this formula here, x of I. Take the beginning left endpoint, add on delta x I total times, add on 1 delta x to find the first x coordinate to plug into the function for the first rectangle, add on delta x a second time to find the next x coordinate to plug into the function for the next rectangle, and so on. After plugging in each of those x coordinates to the function, I now have the respective heights of all the different partitions, all the different rectangles along our interval. We're using rectangles, so take the area by multiplying the base times the height, add all of those areas up, the summation from I equals 1 to n of the respective base delta x times the height f of x of I, and you have an estimate for the total area. How do I turn that estimate into the actual area? How do I decrease the amount of error from using rectangles to get to the actual area? I want to decrease the gap that I am underestimating here or overestimating here. How do I do that to take my estimate and get it closer to the actual area? Rectangles, right? If I squeeze more rectangles, I make delta x smaller and smaller and smaller. If I squeeze more rectangles by adding a great number of rectangles n, I have smaller and smaller underestimates and overestimates. Gap that I'm underestimating here versus overestimating. The total area is therefore the limit of that prior summation. The limit as the number of rectangles n goes to infinity of the summation I equals 1 to n of f of x of I times delta x. Brief discussion of our kind of introduction to Riemann sums from yesterday. Let's practice another one. I wanted to do this one because rather than starting with a left endpoint of 0, as we saw in our example of yesterday, we did a calculation of the area under a curve with a left endpoint of 0. Now this function given by y equals x squared minus 3x plus 5 has a left endpoint that's non-zero, starts at 1. What is the area under the curve given by y equals x squared minus 3x plus 5 on the number from 1 to 4? Starting at a non-zero number for your left endpoint makes this a little bit more tough in terms of the algebra we have. Trying to estimate this area shaded. Okay. So, the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. Let's set up our Riemann sum here and start using summation formulas to simplify. Delta x is given by b minus a over n, the width of the interval divided into n different partitions. What are a and b in this particular area question? 4. So 4 minus 1, which is 3. We're going to take a length of 3, divide it into n total pieces. X sub I is a plus delta x sub I. So our a value is 1. Start from 1 and add on 3 over n I times. And go from one partition to the next. Line these together, and it will be 1 plus 3i over n. So using our Riemann sum here with our defined delta x and x sub I, the limit as n becomes infinite of the summation from I equals 1 to n of f of 1 plus 3i over n times 3 over n. With the function notation here, what does that function notation tell me to do with the 1 plus 3i over n? Do the function, right? Replace x with 1 plus 3i over n. One plus 3i over n squared minus 3 times 1 plus 3i over n plus 5. We're going to bring down the same 3 over n for delta x hanging off on the very right. Start expanding. I need to multiply and distribute 1 plus 3i over n times 1 plus 3i over n. See, that's 1. I over n. 3i over n times another 3i over n, that's 9 I squared over n squared. Next, this middle portion here, just working through the expansion of the algebra. 3 times 1. 3 times 3i over n would be 9i over n plus 5. completely altered. Okay, tell me what to do next. Okay, so what like terms can I combine then, Shay? So you're saying 5 plus 1 is 6 minus 3 is 3. And then I don't think anything else combines with this, right? 9i squared over n squared. Still hang on to the 3 over n out the very right. So I can now multiply those two quantities together. Let's distribute the 3 over n times each of the 3 terms in here. Three over n times 3 is 9 over n. 3i over n times 3 over n, that's 3i times 3 for 9i. N and n make n squared in the denominator. Let's see, 9i squared times 3 is 27i squared over n cubed. How many different terms are in that expression? Okay, let's break it up into 3 different sums. Using summation properties, I'm going to break it up into the summation of the first term, 9 over n, the summation of the next term, minus 9i over n squared, and then finally the summation of the last term. See, I might as well also factor out the n's while I'm at it here too. As n goes to infinity, n is going to be a constant. I can also factor out these constants. I can factor out the n, the 9 over n squared, and the 27 over n to the third, because each of those are also just constants. Factor out the constants from our summation. Cube summation of I equals 1 to n of I squared. Basically factoring out what's a constant from each of these terms. 1 over n, 9 over n squared, 27 over n to the third. What should we do next?
Use the rules that we had.
The summation formulas.
Yeah.
Don't we have summation formulas for these sums, these 3 separate sums? I have a summation for the perfect squares from I equals 1 to n, the summation for the integers from I equals 1 to n, excuse me, the summation of a constant from I equals 1 to n. Let's replace those with our summation formulas in terms of n. Let me remember these here. We'll have 1 over n. This summation of 9, n times would be 9n. Is I. Let's see, I'll bring over the minus 9 over n squared. The summation of the integers. Look up that formula. It's
N.
yeah. N quantity n plus 1. I squared. This one I have a hard time remembering. Is it? Bring over the 27 and n cubed first. Is it n plus 1, 2n plus 1? Multiplied by 6. Check my memory. Does that sound reasonable? I think so. All right, more algebra to do. These just get kind of hairy after a while, but let's start cleaning this up. 9n times 1 over n will be what? That one's easy. Just 9. See you later. See, I can multiply these together. 9n times n plus 1. That would be 9n times n, or 9n squared. 9n times 1. 9. 2n squared. Let's see here. 27n, let's just bring that down. We'll multiply n plus 1 times 2n plus 1, so that's 2n squared. N times 1 is n, 2n times 1 is 2n, so altogether that's 3n. 1 and 1 make 1 again. They multiply. Divided by 6n to the third. Gazunda. Let's see what we can do next here. Bring down the 9. Each of these two terms, 9n squared and 9n, are both being divided by what? Each of these two terms are both being divided by what factor? So let's just separate them. Minus 9n squared over 2n squared. I'm also subtracting off this next quantity, so be careful of your signs. I'm subtracting a positive 9 over 2n squared. So when I bring that down, it will be minus 9n over 2. So that'd be an easy place to make a sign mistake. It's like you're subtracting off this entire quantity. (27n times 2n squared). 27 times 54. N cubed over 6n cubed. (27n times 3n is 81n squared. Divided by the same 6n cubed. 1 times 27n, or 27n over 6n cubed. Oh my goodness here. I can reduce some of these down. For example, what's 9n squared divided by 2n squared? Why just 9/2? Shay?
The x squared.
So let's just reduce some of these. Bring down to 9. Minus 9/2. The next term, I have 9n over 2n squared, so one of the n's will cancel out, leaving still 2n on bottom. The next term, 54/6. That's all that's left. I can divide both of those by 3. 54 divided by 3, 18. Actually, no, I can divide them both by 6. 6 divides into 54 how many times? What am I thinking? 9. What am I thinking? Let's see, 81n squared over 6n to the third. I can cancel out 2 of the 3 n's from the bottom. 81 divided by 6. Both divisible by 3, so that's 27/2. So 27 over 2n. On the last term, 27n over 6n to the third, I can cancel out one of the 3 n's. So 27 over 6, divide them both by 3, is that 9/2 again? Writing them each of these ways makes this next step much easier. As I take the limit, as n goes to infinity, are any of these terms going to cancel out? Take the limit. Let n get infinitely large. Which terms are going to stay? Which terms are going to go? So the third term and the last term. I'm looking at those. Yeah. As n gets really big, as n goes to infinity, wouldn't 9 divided by a really, really big number go to 0 pretty quickly? That goes to 0. Same thing here. 9 over 2 times an infinite number squared. Well, that's also just going to be 0 essentially. Oh, I didn't see this. This one also, right? I didn't see the n on this one. That one's gone too. All that's left is 9 and 9 to make 18 minus 9/2. See, I can find a common denominator. 18 would be 36/2 minus 9/2, or 27 times 13.5. Area under the curve is 27/2. I know those are long ones, aren't they? Wait till I show you the shortcut.